Welcome to the lecture on spheres for geometry. We are talking about surface area and volume of spheres here in lesson 12.6. You should know these words and what they mean by the end of this lesson, and also use those extra examples in your book as always to help you out. So let's get started by drawing a sphere. What is a sphere? Here's my favorite sphere in the whole world, at least right now that I can think of, a basketball. I love basketball. And so let's draw a sphere. So the easiest way to draw a sphere is just to draw a circle. That's alright, not my best circle, but that'll do. And then to represent I can't say it, three-dimensionality, the three-dimensional aspect of that, we're going to draw kind of an ellipse type shape inside that three-dimensionality. Woo! Maybe you can say that better than me. I am not doing so well with that. So here's a sphere. This right here, we'll label things in a different color here. This is going to be the radius of the sphere. The sphere is just the set of all points that are the same distance away in 3 dimensions instead of 2 dimensions. 2 dimensions, it's a circle. 3 dimensions, it's going to be a sphere. So this is the radius right there, from the center to any point on the sphere. The point right there itself is called the center, just like it's the center of a circle. It's the center of the sphere. All the way across, it's no different than a circle. Its diameter. So diameter is all the way across. And just like we learned with circles, if you connect 2 points on a circle, if you connect 2 points on a sphere, it's called the same thing. It's called a, do you remember what it's called? Starts with a C. Starts with a CH. You say chord, you're right. So it's a chord. So a chord is just something that's going to connect 2 points on the circle. So a chord, it connects 2 points, or on a circle or a sphere. 2 points on the sphere. Here we're talking about spheres, so connecting 2 points on the sphere. That is what a chord is. And I think that's good in terms of an introduction to the terms of a sphere. And now a formula. The surface area of a sphere. This is theorem 1211. Theorem 1211. We are not going to prove why this is true. I will show you something that helps you remember why it's true. But the proof of this theorem, this formula, and the proof of the formula for the volume, it takes more advanced mathematics than what we know at this point. I remember the first time I saw these formulas proved and actually understood why they were what they were was in calculus, and I thought it was awesome that it always worked out this way. But 4 pi r squared is the formula. To help you remember that, this is not a proof, remember, but to help you remember that, here is an example where we're talking about, or we're looking at a baseball, and you can see here that the baseball, if you, maybe you did this as a younger kid, I don't know, but maybe you pulled a baseball apart. Maybe you ripped out the seams, pulled that apart, and you got something that looked like this. This is the net for a sphere. This is what it looks like two-dimensionally when you rip it apart. So notice there's one circle here. There's a bit missing right here, but that would get filled in with this extra part right here. So what you got here over the circle would get filled in right here. You could do the same thing here, here, and here. You could basically make 4 circles. The part that's overlapping here could get filled in here, and you would end up getting a whole sphere like that. The surface area, the area of the surface, is what it would take to wrap around the baseball like that. And so from there, we have what we need for us to hopefully remember that that's the formula, that is what it is. So surface area of a sphere, 4 pi r squared, 4 circles in other words. 4 pi r squared is 1 circle, so 4 pi r squared. And then let's draw another sphere, but I want you to draw, let's draw it like this. And let's imagine there's a plane intersecting this sphere right here. And you know what, let's draw this in our different color. So let's take our different color, draw this carefully, you might just want to watch until you see me finish this right now. So in our different color, we'll draw the plane that's intersecting this. Wouldn't actually be able to see that part, so let me make that part hidden. Okay, so this intersects the sphere, and where it crosses, where it cuts through there, would be just this part right here. So shade in this part. This is the cross section created by that plane cutting through the sphere. And this right here is called a great circle. What makes it so great? Well, it's pretty much the biggest, it is the biggest circle you could make in the sphere. The great circle, it contains the center of the sphere. So it's great circle. This is a definition of that. It's the intersection of the sphere and the plane containing the center of the circle. And there's one more definition I want to throw in here. I think I can squeeze it down right here. It's a pretty quick definition. A hemisphere. All you really need to know to get that is that it's half of a sphere. So a hemisphere is half of, there we go, half of a sphere. And so let's talk a little more about those two things and then we'll move on here. So over here, this might be a better picture of what you see here. This plane, there was a plane, or maybe you took a knife and sliced that right down the middle, right through the center, include that center point. This right here would be an example of a great circle. I could slice it this way, just like this. I got sliced this way. You'd have another great circle right there. You'd have a great circle right here containing the center. And notice these are cutting the spheres in half. You have the northern hemisphere and the southern hemisphere of the Earth. Here you have the western hemisphere and the eastern hemisphere of the Earth as well. So these are examples of hemispheres. The ones we're probably most used to hearing about is half of the Earth. So let's move on to an example now where we use that formula to figure something out. So let's draw a sphere to begin. And let's draw a circle here. And then let's draw another circle. This is a great circle because it's cutting that sphere in half, as including the center. But I want you to draw another great circle. So it's going to be kind of an ellipse, but off to the side here, like that. So just so we know, it doesn't always have to be going horizontally like that. This is going to have a circumference, C, of 24,875 miles. So that's the circumference of a great circle. And my question to you is, what is the surface area? And so we know that surface area is 4 pi r squared. I'm going back to that formula. So I'm going to write that down over here. The surface area is 4 pi r squared. However, I don't know my radius right now. If I knew that, it would be very easy. I would just plug it in. However, though, another however, again, I know the circumference, and I know the formula for circumference is supposed to be that C, circumference, equals 2 times pi times r. So I'm just going to plug that in right down here. So that's how this problem will flow. We'll take that, we'll plug that in right there. We've got 24,875. I'm going to have this equals 2 pi r. I can take both sides, divide it by 2 pi. That'll go away there and there. And I'm left with that the radius, if you round this off, it's very, very close to 3959. And I just want to take a moment to verify that. Let's click on the calculator there. There we go. So dividing this by 2 pi, I'm going to put 2 times pi in parentheses so that I don't divide by 2 first. I want to multiply 2 times pi first. So 2 pi is going to end up being, nope, that did not do it for me. That's no good. Start over. Okay, 24,875 divided by, what the heck, clear that, 24,875, there we go. I think I should be able to do it now, divided by 2. I'll put times this time. I thought it would do it for me without hitting times, but it did not. So 2 times pi, that's 2 times pi, dividing that there. That gives me very, very close to there. If I'm rounding off to the nearest tenth, that would be 0.0 right there. So I'm going to say to the nearest tenth, I'm going to say that's a good value there. And let's go from there. So this is in terms of miles. So this many miles is my circumference or my radius. Now I'm going to take that value, I'm going to plug it in up here. So it's flowing from here. I figured out the radius. Now I'm going to flow up to here and figure out my surface area. So I have this, and then I'm going to plug in this. This is approximately now because I rounded that off a little bit. And if I put this into a calculator, 4 times pi times that, I have to square that part. I'm going to get 4 pi times, this squared is about 15,600, or 15,673,681. And if I multiply this times 4, I would get 62,694,724. Yes, there's a little bit of rounding error here because I rounded this to nearest tenth. I could have used more decimal places. It might be a good idea to actually do that here, but I'm going to say it was okay. I'm going to say that you were allowed to, in the directions for this question, you were allowed to round the radius to the nearest tenth of a mile. So if we did that here, we plug that in like that, it would look like what we see here. And this would be an exact answer, this many miles squared. But this would approximately be, multiply that times pi, you get about 196,961,284 approximately miles squared. So yes, it's an approximation in both cases. But where is this coming from? Why is this? Why did I use that number? Why is that an important number? Well, you may not have known this, but that's the approximate radius of the Earth, actually. 24,000, or circumference of the Earth, 24,875 miles. So I get this as my radius, I plug that in. This is the area of the surface of the Earth. About 75% of that is water, and about 25% of that is land. So if you're into geography, you have about that much land, 25% of that value. You can fit however many people per square mile. You could figure out the population density of places that way, of the whole Earth that way, and how many people are fitting into a square mile. Cartographers, people that make maps, would be interested in this kind of data as well. But let's move on to the other formula, and the formula for volume, and then one more example. So the volume of a sphere, that's the other big guy for this lesson, the volume of a sphere. This is theorem 1212. And that is not one we're going to prove. This is not one that I'm even going to try to explain at this point. It takes some calculus. That was, again, the first time I saw this proved why it's true. But 4/3 pi r cubed. This is a formula you'll just have to remember is true. So 4/3 pi r cubed. You can keep the volume one straight from the surface area one because volume is in units cubed, and this has r cubed in it. And then if you can just remember that baseball to help you as an example. So we had the baseball here, splitting that into 4 congruent, or 4 circles that have the radius of an r, 4 pi r squared. Keep that straight. You've got 4/3 pi r cubed for the volume instead. And so let's assume the following have the same volume. We're going to draw some pictures in just a moment. So assume the following have the same volume. What is the radius of the sphere? So our first picture, we're going to draw a cylinder. The cylinder, let's draw it on its side though. So this is I don't think we've drawn one like that before, but let's say we have a cylinder on its side, and there's the part you can't see right there. We're going to say that this radius from there to there is going to be 2 centimeters, and the distance from there to there, the height of the cylinder, in other words, is 16 centimeters. And then we've got this sphere over here, has the same volume as that. So if you filled this up with water and you filled the sphere up with water, they would hold the same amount of water. But we're trying to figure out what's the radius of that sphere. That is awful. Come on. There we go. So the radius is an unknown quantity. And if these have the same volume, we can start here. We know that the volume of a cylinder, this is a cylinder here, this is a sphere, volume of a cylinder is supposed to be pi r squared, the base, which is a circle, times the height. So I have pi times r is 2, so 2 squared times 16. That's going to be 4 right here. 4 times 16 is 64. So you have 64 pi for your volume. Might as well leave it like that. That's an exact answer. That's the best answer you can possibly get. And then take that and plug it into the volume formula for a sphere. You've got 4/3 pi r cubed. We're trying to solve for r, so plug in 64 right here. 64 pi. Now from there, how can we get rid of fractions like this? We can multiply by the reciprocal. We can multiply by 3/4. So I'm going to multiply both sides by 3/4. That will cancel with the 4/3. And then we take this times 3. You can make this a fraction. You can put that over 1. I could reduce this by making this 16 and a 1. So I'd have 48 on the top. I'd have a 1 on the bottom. That's just 48. So I have 48 pi equals pi r cubed. So the nice thing here, I notice I can divide by pi on both sides, and the pi's will cancel both places. And so I have 48 equals r cubed. So we've seen stuff like this before quite a bit, where we had r squared here, and we took the square root. But now we have r cubed. Is there such a thing as a cubed root? There sure is. We make that same symbol as a square root. Square root, it's assumed there's a 2 right here, invisible 2, if you don't write anything. But if I write another number, I'm taking the cube root. If I wrote a 4, it's the 4th root. A 5 would be the 5th root, and so on. So I'm going to take the cube root. A cube root will undo a cube. And so my final answer here excuse me, is going to be that r is going to be approximately, I just need to type in the cube root of 48 into a calculator. So 48, another way to write that would be raising that to the 1/3 power. So you could think of it like that. Mine happens to have a cube root button right here too, so I'm going to just hit that. This would also work too if I hit that and put a 3 in for the y variable. So different calculators will look a little different. We'll talk more about that in class if you're one of my students, as to the best way to type it into your calculator. But I'm just going to hit the cube root button since I have one of those. And so that means 3.63 approximately times itself 3 times would be 48. So I have 3.63 approximately as my radius. That is in terms of centimeters. That is my final answer there. And that'll do it for us. Nothing more to say. Check out the examples in your book for some extra help. And make sure you got those terms down. I think we should have explained all these things by the time we've gotten through this lesson. Yep, we should know what all these things are at this point. So hopefully that helped you out, and I hope you do well on the classwork. And if you get tested on this, hope you do well on the test as well. All right, have a good day, everybody, and I will catch you later.